Hi class, today we're going to talk about complex numbers. Our warm-up is to find, our warm-up is to find the zeros of y equals x squared plus 4x plus 5. To do this, remember when you're looking for the zeros, we want to know where is the function equal to 0, where is y equal to 0. And we're looking for the x-intercepts of the graph. So one method we can use to find the zeros is the quadratic formula. So first you want to identify your a, b, and c values. A is the coefficient of x squared, which is 1, b is 4, and c is 5. Then we're going to plug into the quadratic formula 1, 4, and 5 for a, b, and c. And so remember the formula, x equals opposite b, so negative 4, plus or minus the square root of b squared, 4 squared, minus 4 times a times c, all over 2a. Okay, so if you simplify this, you have negative 4 plus or minus the square root of, this would be 16 minus 20, so negative 4 divided by 2. If you try to do square root of negative 4 in your calculator, you get an error because you can't take the square root of a negative number. So this is a problem. So at this point, we're going to have to write no real solution. Now, if we take the same equation and graph it, you get this graph right here. So it asks how many solutions are there. When you look at the graph, you look for the x-intercepts. So when we talk about solutions, another term for that is x-intercepts. And another term for x-intercepts is the zeros. So the zeros of the function are the same as the solutions or x-intercepts. Or another term even yet is roots. If I'm looking for the roots of the function, I'm looking for the zeros or the x-intercepts or the solutions. And so looking at this graph, we see that it doesn't cross the x-axis at all. So therefore, there are no real solutions. Well, this has bothered mathematicians for a long time. They want to have an answer. So in order to solve quadratic equations like this in the warm-up, where there's a negative number under the square root, mathematicians decided to expand the number system. So if a number isn't real, then it is, you guessed it, imaginary. Whoops. Imaginary. So mathematicians created imaginary numbers. So if I took the square root of negative 25 and put it in my calculator, it would say error. So let's say we broke up 25 into negative 1 times 25 and wrote it as a square root of negative 1 times the square root of 25. Well, here I can simplify that to be 5, but what do we do with the square root of negative 1? There is no real number that can be squared to produce negative 1. If you try to square negative 1, negative 1 squared would be the same as negative 1 times negative 1. Well, negative 1 times negative 1 actually would equal positive 1. So you can't get a product of a negative number when you're square. So therefore, they decided that square root of negative 1 will equal the number I, the imaginary number I for imaginary number. And if we square that equation, square both sides of it, you get that I squared, and if you square this right here, the square root of negative 1, if you square it, equals just negative 1. Right? The square and the square root cancel each other out, and you just get negative 1. So this is our definition of imaginary numbers. Whenever you see the number I, you need to remember that it equals the square root of -1. So back to our previous problem there, it said square root of -25. We can simplify that using i's now. That's the same as saying square root of 25 times the square root of -1. Square root of 25 is 5. Square root of -1 is also known as I, so this is equal to 5i, the imaginary number 5i. Okay, so imagine you're taking turns, right turns, and you're starting by facing the direction of north. So we have north, south, east, west. So if I'm facing north and I make one right turn, now I am facing east. If I take 2 right turns, I'll be facing south. If I make 3 right turns, I'll be facing west. If I make 4 right turns, I'm facing north again. And if I make 5 right turns, I'm facing east. So it starts the cycle over. So every 4 turns, I'm back to where I started. So if I was at the first right turn, I was east, and then the 5th right turn, I was east. Every 4 turns, I'm back to the same position. It works the same way with complex numbers. We know I is just I, right? Or square root of -1. If I square it, we get -1. If I did I to the 3rd power, that would be the same as I times I squared. I times I squared equals I to the 3rd. So if you simplify that, that's the same as saying I times -1. So I to the 3rd is the same as saying -I. I to the 4th power. Another way to write that is I squared times I squared, which is the same as saying -1 times -1. And -1 times -1 actually equals +1. So it simplifies to +1. Well, what about I to the 5th? Well, I to the 5th is the same as I to the 4th times I. I to the 4th we just figured out to be 1. So that's 1 times I, and 1 times I is I. I'm back to the same thing I got for I to the 1st power. Sorry, my Mobi's freezing up. Just 1 second. There it goes. Okay, so as you can see, every 4th power, you're back to the same simplified answer. So I to the 6th, if I kept going, would be the same as I to the 2nd. It would equal -1. I to the 7th would equal I to the 3rd. Every 4 powers, it equals the same thing. Okay, so that's an interesting pattern that you see when you take powers of I. Okay, so let's work with simplifying some of these square roots. So, for example, it says simplify. We don't want to leave a negative under the square root like this. So when you simplify it, break it up, this number. Break up square root of -9 into square root of 9 times the square root of -1. So square root of 9 we know would be 3. Square root of -1 would be I. So this is the same as saying 3 times I, or 3I. The second one here, again, break up square root of -10 into square root of 10 times square root of -1. And now we write square root of -1 as I, so we get -3 plus square root of 10 times I. You notice the second answer has both a real number and an imaginary number in it. The first one was just an imaginary number, but this is a combination of a real and an imaginary number, which is a different type of number that we're going to talk about. It's called a complex number. Whenever you have a complex number, it's a combination of a real and an imaginary number. It's always written in the form a plus bi, where a and b are real numbers. The a is the real part of the number, and the bi is the imaginary part of the number. So now we've expanded our number system to include imaginary numbers and complex numbers. Let's see how they're all related. So here's a tree diagram showing the relationship between all these different kinds of numbers. If we were to match these up here at the top you see 3 plus 4i, that would be a complex number like we just talked about. All numbers are some types of complex numbers. Okay? The complex numbers could be broken down into the real numbers over here or the imaginary numbers. And if you have real numbers, they can be broken down even more. Over here on the left side we have numbers that can be written as a fraction. Those are called rational numbers, from the word ratio, which means fraction. So ratio, numbers that can be written as a fraction. And if they can't, then we call them irrational. That would be numbers like pi or square roots of numbers that go on forever and don't have a pattern. They can't be written as a fraction, or the number e is another irrational number. And then a more specific kind of rational number are these numbers that don't have decimals. The numbers on the number line, those are called integers. And then if you're just talking about positive numbers, those are our natural numbers, our counting numbers. So natural numbers would be considered integers, rational numbers, real numbers, and complex numbers, everything above it in the tree diagram. When we work with complex numbers and simplify them, you just need to remember that you combine like terms, just like you would do in regular algebra with x's and constant numbers. You combine the like terms. You combine the real parts together, and then you combine the imaginary parts together. So if we're adding, we actually don't even need these parentheses because you're adding and you're just adding your like terms. So it's like saying 4 minus 7i plus 10 plus 6i. Okay? So when you're adding, add the real parts. 4 plus 10 is 14. Then add the imaginary parts. Negative 7i plus 6i would be negative 1i, or just negative I. And you've written your answer in a plus bi form as a complex number. Second one, just when you see those parentheses and you're subtracting, make sure you subtract both terms. So you have to distribute that negative sign to both of these. That's really important you remember to do that. So this is the same as saying 7 minus 12, and then this becomes minus negative 8i becomes plus 8i. And then combine the like terms. 7 minus 12 is negative 5 plus 8i. That would be the simplified answer. And then the last one, same thing. You want to, just same as what we do in algebra, you multiply each part of the complex number by 4. So 4 times 13, that would give you 52. 4 times 3i is 12i. And then bring down the 6i. Combine your like terms, you get 52 plus 18i. Okay, so multiplying complex numbers. Again, same thing as we do in regular algebra. Like you can distribute the 6 to both parts of the complex number. 6 times 10 is 60. And 6 times negative 5i would be negative 30i. And that's simplified. Next part, you could either use the FOIL method, first, outer, inner, last terms, or make a box, which I kind of prefer to do. And multiply on the one side, put 2 minus 3i. On the other side of the box, on the outside, put 4 plus 7i. So you're multiplying these two numbers together. So start with 4 times 2, we get 8. 4 times negative 3i is negative 12i. 7i times 2 is 14i. And the last box, 7i minus 3i is negative 21i squared. I squared. So if you write out your terms, you have 8 minus 12i plus 14i minus 21i squared. Now we want to simplify this more. You need to remember that I squared is equal to negative 1. So whenever you see an I squared, we want to simplify that term more. 21 times I squared would be negative 21 times negative 1. There's a minus there you need to bring down. And then you can combine these two terms together. So negative 12 plus 14 is positive 2i. And so this, negative 21 times negative 1, becomes positive 21. So we have 8 plus 2i plus 21. And now you can combine the real numbers together. 8 plus 21 is 29 plus 2i. And that's the simplified answer. And then the last one down here at the bottom, I'm going to take a picture of it so I have a little more room. Okay, this one, when it's squared, you need to remember that this is the same as saying 2 minus 3i times another 2 minus 3i. Squaring, you multiply the number by itself. Okay? So again, this is another one where you would multiply using the box or FOIL. So I'll put 2 minus 3i on each side of my box and multiply it out. 2 times 2 is 4. 2 times negative 3i is negative 6i. Negative 3i times 2, negative 6i. And positive 9i squared. Write out the terms that you get. 4 minus 6i minus 6i plus 9i squared. Combine like terms, we have 4 minus 12i. Remember, I squared equals negative 1, so we can write 9 times negative 1 here, which is negative 9, plus 4 is negative 5 minus 12i. Make sure you don't square each part of this. This is not equal to 4 minus 9i squared or 4 plus 9i squared. You cannot distribute the square. You've got to write it twice and multiply it out using the box or FOIL. And the last part here is you need to understand what conjugates are. This is a new term. When we talk about the conjugate of a complex number, you take the number and you keep the same real part, but then you write the opposite of the imaginary part. So the conjugate of 3 plus 2i would be 3 minus 2i. So 3, the real part is the same, and the positive 2i becomes negative 2i or minus 2i. Okay, so that's the conjugate. The next one, same real part, negative 4, and then instead of minus 5i, we write plus 5i. That's the conjugate. And last, we have positive 10i. So the opposite of the imaginary would be negative 10i. That's the conjugate. Okay, I believe that is it for this lesson. So go ahead and do the next page in your packet for homework, the Day 1 worksheet on complex numbers. Have a great day.